Hello and welcome to USMA Orgo. We're now on Chapter 9, so we skipped a few chapters to get into Chapter 9 so we can actually learn some about the instrumentation that we can use to identify organic molecules. So now you have a little bit of a knowledge of organic molecules. Now we want to be able to use that knowledge in the actual lab and identify some organic molecules. So that's why we jumped to Chapter 9. And we also do Chapter 9 a little bit out of order. First thing we want to talk about is mass spectrum. So basics with mass spec is we have an ionization source that fragments the molecule, and then those fragments then race to a detector, and then the detector gives us a reading of the amount of each fragment that we see. So the key here is you're going to get the information on the molecular ion, and you're going to get information on the key fragments. So for example, we have hexane down here. So the simplest fragment that would happen is when it gets ionized is that you lose one electron. So this annotates the fact that we lose one electron, and that's called the molecular ion. So it's all of hexane minus one electron, and this one, the molecular weight of that, which is written as Mz, is equal to 86. So if you see a peak for 86, you can tell that you have hexane. And then you'll also see peaks for fragments that are common to this molecule. So if you lose, say, one methyl group, the molecular weight will be 71. You lose two, an ethyl group would be 57. You lose a propyl group, and you get 43. And then you'll see a fragment of the other half of these two would be 29. So let's look at an actual mass spectrum. So again, I have this box up here, which is from the previous slide, to keep in mind what the different fragments are. But so this is what a mass spec will look like, and usually the furthest to the right peak that you can see is usually the molecular ion, which gives you a lot of information in that you know the molecular weight. So if you had an empirical formula, you confirm that the molecular formula is what you think it is by using the molecular ion. And then you can look for some key fragments. So for example, we have a 71, which lines up to the 71 up here, which tells us that we lose one methyl group. And you also can see the base peak is 57, or the loss from here to here of two carbons, so an ethyl group, and the molecular weight for that is 57. So the base peak is nothing more than the most common fragment. So as you see on the left-hand side, we're talking about the relative ion abundance. So that's the one that the detector sees more often than not, is that fragmentation. So there's a lot more information you can get out of mass spec. You can study different splitting patterns, different breaking, different fragmentation, but the basics are, if you can get the molecular ion and some information as some key fragments, that'll help you figure out what molecule you're dealing with. So then we move into NMR. So there's several different types of NMR. There's hydrogen or proton NMR, there's carbon-13 NMR, there's even different other atoms like nitrogen or phosphorus. And there's also two-dimensional and correlation NMRs that we'll talk briefly about. The one that we'll spend the most time on is proton NMR. And the information you can get from a proton NMR is the number of different types of hydrogens. That's the number of signals you'll see, and we'll look at a spectrum on the next page. You could also find out the number of adjacent hydrogens, which is a splitting pattern that we'll talk about. And then you can get the chemical environment around that hydrogen, which tells you what it's connected to. And then you can also find out how many hydrogens a signal is due to, which is the integration. So let's look at a spectrum. So this is a simple spectrum of ethyl bromide. So there's two signals. They're blown up on the left-hand side here so that you can see them a little bit closer. The first thing you look at is where they appear on the spectrum as far as from left to right. This is the parts per million. So the closer to 0 they are, the more they're like just plain alkanes. Okay, and normally when you run NMR, you have TMS, which is trimethylsilane, which is used for an internal standard. So that always shows up as 0, so everything else can be measured against that. So if you look at this, you have 2 signals, so that means you have 2 chemically different protons. And then if you look closer, you can see that the number of peaks will give us some information. So for example, this has 4 peaks in that signal. So we have what's called the n+1 rule. So that means that there are the number of hydrogens plus 1 gives us a number of peaks. So for example, this peak is due to these 2 hydrogens right here. So those 2 hydrogens have 3 hydrogens next to them. So n+1 would be 4. So that's why we see those hydrogens show up as a quartet or 4 peaks. And then likewise we have these red CH3. They show up, they're surrounded by 2 hydrogens, so n+1 would be 3, so that's why you see a triplet there. So again, the splitting pattern gives us how many hydrogens are next to it. Where it is on the spectrum tells us what's next to it. So for example, because the blue one is closer to bromine, it's going to fall further down the spectrum than further or higher in number than the one that is further away from the CH than the bromine. So the position is based off of what it's next to. And then finally the integration, which is down here, or sometimes you'll see it written on top of the peak. That tells you how many hydrogens that signal is due to. So that means that this signal has 2 protons that are making that signal are chemically equivalent. And as we can see, those are the 2 there. Same thing, we have the 3 on this side. So there's a lot we can learn and practice with NMR. There's a lot of new stuff, and I encourage you to get into it and practice it so that you can figure out. And it's kind of fun after a while because it's like a puzzle to solve. So you don't have to memorize where things show up. We kind of have this in your RDC, which kind of shows you the relative areas that you tend to see things. So say, for example, double bonds, protons will be, around 4 to 6.5. And then aromatic protons, as you can see, are going to be, between 6 and 8.5. You have aldehydes and ketones, aldehydes or carboxylic acids, they're going to be way out here between 9 and 12. So this is in your RDC and gives you some information as to where you might find some of the peaks. So moving on to the different types of NMR, we have carbon NMR. So that gives us a number of chemically different carbons. The difference here is that you don't get splitting with carbon-13. So really you get the number of different types of carbons you have, and then the shift gives you some information about the environment. So the example we have here, you can see that you have 4 different types of carbons. So if you look at this molecule, there's 1, 2, 3, and then these are both the same, so they both count as 4. So, and the only other thing you can really tell is the fact that this carbon, or CH2, is further to the left, so that one's probably number 1 because that is closer to the bromine, so that'll show further down the spectrum. Again, a lot of new information, study, practice, and we'll talk a lot more in class. So I'll move on to DEP carbon NMR. So DEP basically takes your signal, your carbon, so this has 1, 2, 3 carbons. So you have 3 signals here. And so they correspond to the ones that they're talking about over here. But when you use DEP, they actually take, okay, the CH3 signal shows up by itself. So we know this one is a CH3, so that's number 3. This one is it shows only the CH2 signal, so the CH2 signal is actually, so that would be our number. So this is our number 3, this is our number 1. And then the final one is a CH signal, so that would be our number 2. So if you want to go back and correct up here, it'd be 2, 1, and 3. So the depth helps you figure out particularly where they're kind of close to each other, which one's which. Then you can actually go with the two-dimensional NMR. So COSY has a proton NMR versus a proton NMR, and then the places where they intersect actually give you information about what's next, what hydrogen's next to that hydrogen. So we'll talk about that more in class. And then finally, you can do het core, where you take a proton NMR and it goes against carbon. So then where these intersect, you can say this hydrogen is on this carbon. So that gives you more information about the structure. So I know that spectrum is all new to you, so it's going to be a lot to learn here. So take the time to read the lesson and do the problems, and we'll do a lot of practice and ask questions in class. There's a little bit of a description on page 455 on describing proton NMR, and then page 456 quick reference charts for NMR, which are the ones that are on your RDC. Can't wait to work on some of these in class. See you then.